Language models are powerful reasoning engines, but they are stateless and cannot access external systems by default. Function calling, also called tool use, allows a model to request the execution of defined functions, giving it access to databases, APIs, and real-time data it would otherwise be unable to reach. In this video, we explore how function calling works, the concepts that underpin it, and the real-world applications it enables. Let us examine why function calling is such a transformative capability and how it changes the fundamental relationship between a language model and the systems around it. 5 key mechanics define how function calling extends a language model's capabilities beyond text generation into real-world action. When function calling is enabled, the model does not always respond with a plain text answer. Instead, it may output a structured function call, a JSON object specifying the name of the function it wants to invoke and the arguments it wishes to pass. This is not arbitrary output. It is a deliberate decision by the model based on its assessment that invoking a tool is the best way to address the user's request. The structured format ensures that the function call can be reliably parsed and executed by the application layer, maintaining a clean interface between the model's reasoning and the system's execution environment. Once the model emits a function call, execution responsibility shifts entirely to the developer's application code. The application parses the function call, validates the arguments, invokes the actual function, which might query a database, call an external API, run a calculation, or fetch a file, and captures the result. This separation of concerns is intentional and important. The model decides what to call and with what arguments, while the application controls how and where the function actually runs, giving developers full control over execution security, rate limiting, and error handling. After the function has been executed, the application returns the result back to the model as part of the conversation context. The model then uses this result, which might be a weather reading, a database record, a calculation output, or an API response, to formulate its final answer to the user. This two-phase interaction, where the model requests information and then reasons over the response, is what makes function calling so powerful. The model's final output is grounded in real, current, system-specific data rather than relying solely on its training knowledge. Parallel function calling allows the model to request multiple function executions simultaneously rather than sequentially. When the model determines that it needs several independent pieces of information to answer a question, for example, the current weather in 3 cities, it can emit multiple function calls in a single turn. The application executes all of them concurrently and returns all results together, dramatically reducing the total latency of multi-tool interactions. Parallel function calling is a significant practical optimization for building responsive AI-powered applications that rely on multiple data sources. Tool schemas are the interface contracts that tell the model what functions are available, what each one does, what parameters it accepts, and what types those parameters must be. Written in JSON schema format and provided to the model in the system prompt or API call, tool schemas serve 2 purposes simultaneously. They inform the model's reasoning about when and how to invoke each tool, and they constrain the model's output to conform to a structure that the application can reliably parse. Well-written tool schemas, with clear descriptions and precise parameter types, are the single most important factor in determining how accurately and appropriately a model selects and invokes tools. For essential terms that define the mechanics and design of function calling in modern AI systems. A tool schema is the specification that makes function calling possible. It is a structured document, written in JSON schema format, that describes a function in terms the model can understand and use in its reasoning. A good tool schema includes a clear name that conveys the function's purpose, a detailed description that explains when the model should choose this tool over alternatives, a definition of each parameter including its type and whether it is required or optional, and an enumeration of valid values where appropriate. The quality of tool schemas directly determines the reliability of function calling. A poorly described tool will be invoked incorrectly or at the wrong time, while a precisely specified tool will be selected and called accurately across a wide range of user requests. Structured output is the mechanism that allows a model's decision to invoke a function to be reliably translated into a machine-executable instruction. When a model generates a function call, it produces a precisely formatted JSON object rather than natural language prose. This structured format ensures that the application layer can parse the function name and arguments without ambiguity, validate them against the expected schema, and execute the function with confidence that the inputs are well-formed. Modern AI APIs support strict structured output modes that constrain the model to only emit valid JSON conforming to the tool's schema, virtually eliminating parsing errors in production systems. The tool result is the payload that closes the function calling loop. After the application executes the requested function, it formats the result as a message in the conversation, typically a JSON object or a plain text response, and returns it to the model. The model treats this result as a new piece of context and uses it to reason toward a final answer. The quality and structure of tool results matter. Well-formatted results with clear field names make it easy for the model to extract the relevant information and construct accurate responses, while ambiguous or error-prone results can confuse the model and degrade output quality. Designing tool results with the model's reasoning process in mind is an important engineering consideration. Parallel tool use is a performance optimization that becomes essential as AI applications grow more complex. In a naive sequential implementation, if a model needs 3 pieces of information to answer a question, it must call the first tool, wait for the result, then call the second, wait again, and finally call the third, with total latency equal to the sum of all 3 round trips. With parallel tool use, the model emits all 3 function calls in a single response. The application executes them concurrently, and all results are returned together in one pass. This architectural pattern can reduce multi-tool interaction latency by 60 to 80%, making the difference between a responsive user experience and an unacceptably slow one in production applications. Let us now look at where function calling is being deployed to connect AI reasoning to live systems and create genuinely useful automated workflows. From consumer assistance to enterprise automation, function calling is the mechanism that grounds AI responses in real data and enables AI to take consequential actions. Weather and calendar lookups were among the first production deployments of function calling in consumer AI assistance, and they illustrate the pattern at its simplest and most reliable. When a user asks an assistant about tomorrow's weather or their schedule for Friday afternoon, the assistant calls a weather API or calendar API, retrieves the relevant data, and incorporates it directly into a conversational response. These lookups are low risk, easily reversible, and require only read access to external systems, making them an ideal entry point for organizations building their first function calling integrations and for demonstrating the capability to stakeholders. Database queries represent a significantly more powerful and enterprise-relevant application of function calling. Rather than being limited to the general knowledge baked into the model's training, an AI system with database query tools can retrieve personalized, up-to-date information specific to each user: account balances, order history, product availability, contract terms, or employee records. This grounding in real organizational data is what transforms a general-purpose language model into a system that can deliver genuinely personalized and accurate responses at the scale of an enterprise's customer or employee base. Payment processing and booking execution through function calling moves AI systems from the read-only world of information retrieval into the read-write world of consequential action. An AI travel assistant that can search flights, check availability, and actually book and pay for a ticket, rather than merely providing a link, delivers a qualitatively different user experience. These high-stakes use cases require careful design of the human-in-the-loop approval workflow, robust error handling and rollback mechanisms, and strict security controls on the functions that can modify financial records, as mistakes are not easily reversed and the business and legal consequences of errors can be significant. Multi-tool orchestration represents the frontier of function calling complexity, where the model must reason across multiple tools in sequence to accomplish a goal that no single tool can address alone. A customer support agent handling a complex refund dispute might call a tool to retrieve the order record, then a tool to check the return policy, then a tool to calculate the refund amount, then a tool to initiate the payment, and finally a tool to send a confirmation email. all within a single conversation turned from the user's perspective. Orchestrating multiple tools reliably requires careful schema design, robust error handling when individual tools fail, and systematic testing of the full tool call sequence under realistic conditions. Let us bring together the essential points from our exploration of function calling in AI. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.